So DJ Spit unfortunately stained my whiteboard. It's not permanently stained, but as you can see, it's left a purple haze on it, which means I have to get some sort of cleaner out to properly clean it off. Apparently that marker was like really old or something, I don't know. So there's no picture this week. But unfortunately, I'm still fat, so it's gonna be a while before I get back to skinny grad student. So it's been a week since my last video, and I want to make these videos more frequently, but you know, time kind of flies when you're having fun. But I thought I would talk a little bit about what's been going on. And I thought a reasonable thing to do would maybe go over a test I wrote. So just so you know, I'm teaching a pre-calculus class this week. I have to be delicate with what I say because I'm pretty sure some students have found my YouTube channel, and I don't want to say anything that embarrasses anyone, including myself. The test that you see here is the Module 2 exam. They're called modules in the textbook. It's just chapter, so this is the Chapter 2 test. And when I write these tests, I typically choose 10 problems, and I try and make these problems as basic as I can without, but not too basic. I don't want to ask completely trivial questions, but I do want the average to be a certain amount, preferably something in the 70s. I believe from memory, the average grade for this test was 72% roughly, somewhere in there, which is pretty good. So what do these questions ask? The first question really is me testing whether or not they know what this word quantity is. And question 2 is whether or not they can distinguish between a fixed quantity or a varying quantity. So questions 1 and 2 are kind of gimme problems. I want everyone to get something. I don't want to give anyone a 0 on this test. Question 3 is about finding the equation of a line that passes through 2 points. Specifically, I want it in y-intercept form. So it kind of tests whether or not they know what y-intercept form is. Question 3 is more or less the same. You can see that my Sharpie marker kind of bled through the paper, unfortunately. But it's like question 3. I want them to come up with the equation of a line that's in point-slope form, and then tell me what the y-intercept is. Question 5, I don't know where I said 3, is a word problem, where they have to come up with the equation of a line and then answer some questions about it. Which means, can they take this information I give in paragraph form and make a mathematical statement about it? Question 5 or 6 is more or less the same, but I use the delta notation, so it kind of tests whether or not they know what that means. But there's nothing really difficult about 5 and 6. And then what do we have on the next page? Question 7 is true-false. It's been a while since I looked at this test. I typically don't recycle tests. I write a new one every year. So it's okay, I'm showing this. True or false? So this is about proportionality. I know that my course coordinator, because there's a bunch of us that teach pre-calculus, she tends to emphasize that we need to distinguish between linear relationships and proportionality of 2 variables, meaning that if 2 variables are proportional, then they are related to each other by a linear equation, but not vice versa. So that's kind of the purpose of question C here, because every time we give the final, a majority of the students miss that question. I don't know if it's based on like how the question's worded or what, I'm not sure. But this semester I tried really hard to make sure that they don't make that same mistake. So I emphasize it here. I like to put bold letters and underline stuff to make things more clear. Typically, I don't really like the word problems that I give in these tests. Mostly because that's my own flavor. You know, excuse me. I like problems that are more like, here's an equation and I want you to do something with it. Whereas a word problem is, okay, I gotta sift through the English and then figure out what exactly it is I wanna solve. So questions like 8, 9, and 10 are more my speed. Find the average rate of change of a polynomial over an interval. Okay, that's pretty simple. You just gotta know the formula, and then the center of a circle is this point. This is located on the circle. Give me radius and equation of circle. So we talk about a number of different things in module 2. And then question 10 is about an inequality. And apparently someone has written on this, and it is not correct. I'm not entirely sure what's going on here, who wrote it. You know, when I flipped through this, I saw that and I didn't really pay close attention to it. But now I'm looking at this as like, did I write that? And I'm like, no, I definitely did not. Because 1, it's very wrong, and 2, it's not my handwriting. So I'm not entirely sure who wrote that. Probably a student of mine, but I don't know which student. So that was the Module 2 exam. Module 3, this one they took, I think, like a week ago, and it's more about functions and function notation. And the Module 3 exam tends to be, historically speaking, the one that students struggle with the most. And then Module 4, which is the test they're going to take in a week, is goes a lot smoother for them. They tend to understand Mod 4 better, which is about exponential functions. So I'm not entirely sure why, because when I was learning, like when I was flipping through this stuff and preparing lessons and whatnot of what I was going to cover, I always thought that Module 4 was more difficult to understand than Mod 3 stuff, but I guess that's different strokes for different folks, I guess. So what is this test about? The first question is vocab. I give them a definition. They have to fill in the blank. I was originally going to have them define the word for me. You know, I'd give them the word, they write down the definition, but then I chickened out and made it easier. Question 2 is a box problem, and by box problem I mean an optimization problem. The reason we all call it box problem is because the optimization problem always starts with an example using a box, so it kind of gets this, you know, misnomer. But it's an optimization problem. Question 3 is more about, do they understand function notation? Like, can they tell me what A5 means? They don't actually have to compute it. They just have to tell me what it means as an English sentence. Find the horizontal and vertical intercepts. So, do they know how to plug in 0? And do they know how to set something equal to 0? Question 5 is whether or not they can find a domain. And then we have some word problems. Yeah, so it's kind of more or less the same. I try to mimic these problems similar to what other people are doing, because I don't want to go completely rogue, so that my guys are seeing something else that's different. And question 8. So find the average rate of change of this function over this interval. This has to do more with it's a precursor to the derivative from calculus, because a lot of them will go on to take calculus, whether it's business calc or calc 1. So this kind of gets them familiar with how the derivative is defined before they actually do it. Question 9 is composing functions with one another, and question 10 is finding an inverse. So nothing too bad. I like questions 8, 9, and 10. Those tend to be more my speed, what I like to do. And then I gave him a bonus. I didn't give him a bonus on the Mod 2 exam. But this bonus actually came from a friend of mine in the math department. And he actually discovered my YouTube channel. And when he showed me this bonus problem, I thought that was kind of cute. So I decided to put it on my exam as well. I believe one student got the bonus correct. Most did not even try it. They just wanted to leave. But of those that tried it, only one was able to solve it. I believe the average on this test was 70%, which historically speaking is really good, because I think most students, or like historically speaking, they get very low averages, like I don't know, maybe 55%, I'm not sure, which is kind of bananas if you think about it. But I was proud of my guys. They got 70. So if they're watching this video, which there might be at least one of them, I think some have discovered my channel. You guys did good. Okay, what else do I want to show you before I get to this thing? I guess nothing really. Let's just go to the poster. So in a week, I'm going to present a poster at a math conference, and this is a printout sketch copy of the poster I'm going to not defend. Defend's not the right word, but just present. You know, a couple of us are going to do it. So I'm pretty excited. I've never done this before, and I kind of like the way the poster turned out. So what is this poster about? Basically, it's about Cantor sets in the complex plane. And you can pause the video and read this stuff if you want. I'm just going to give you a brief overview of what's going on. Essentially, we look at tiles, fractal tiles in the complex plane. So let me zoom in. And we study these guys, and you can do a Cantor set construction. So if you're familiar with the Cantor set, we're essentially applying that same logic here with a restricted digit set. And then you can calculate the Minkowski dimension of this Cantor set. And then, understanding how we can calculate this, we kind of get these two results that show up down here in this final line. So with this definition, we show that for any epsilon between 0 and 1, there exists a zeta such that the Minkowski dimension of this intersection is equal to epsilon times the Minkowski dimension of the Cantor set T. If you've been watching my channel for a while, you'll recall that this was what my thesis was about, was proving that statement. And then there was a follow-up to that statement that we later showed, was that if we let F be the set of all translates, or not translates, but of all complex numbers that we can translate by that give us non-empty intersection, and you let F epsilon to be the set of all those zetas with this property, then if you impose certain requirements on the restricted digit set, we can show that F epsilon is dense in F. So just to recall the definition of density, although if you're watching this video, you probably don't know the definition already. For the real numbers, if I give you any two real numbers, you can always find a number in between them that's in that set. For the complex plane, you can think of it as disks. So we say that F epsilon is dense in F, meaning that if I pick a point in F, and I draw a very small ball around it, no matter how small that ball is, I can always find a point in F epsilon that's inside that disk. And so the crux of this problem is to figure out what exactly, excuse me, I got a text message, how to construct zeta. So if you can construct this zeta, which it's outlined here how you can do it, then the rest kind of falls into place using this proposition. So this was more or less what we did in my thesis, and then this corollary that shows up down here was the big theorem. And I'm just now realizing this is an old copy because there's a typo for MJ zeta down here. That T should be a D star. I noticed that a few days ago before I sent this off to be printed, so I'm kind of glad I did that. Read over it, because as soon as I like moved the paper and then I looked down at this corollary, my eyes immediately went to this T. I was like dang it. But it has been corrected. And then the main result kind of goes over here. I'm a little bit upset about the dead space here, but it's not that big a deal. Maybe I could have put pictures there. But that's the theorem, and then here's kind of a rough outline of what we did. The paper that we ended up writing was about 40 pages or so. And wishful thinking, I kind of hope to take this same idea and then apply it to a different setting and maybe put the letters PhD on that and just be done. Because I do kind of, this math is pretty fresh for me. Like, I forget the finer details, but then as soon as I read through this and go through my paper again, it comes back very quickly, despite having not looked at it for like 2 years. And I think I'm going to give a talk about this over a seminar in a few weeks, because it would be easy for me. I kind of wanted to present a different paper at that seminar, but because of how fresh this was for me, I was like, let's just do this. I'm kind of interested in getting back into this and doing new things, maybe. But I don't know. It kind of depends on what your advisor wants to do. It's a good idea to just do what your advisor wants you to do, more so than what you want to do, because they have more wisdom and they can probably help you a lot faster than if you just went out and did your own thing. But, you know, that kind of depends on a lot of things. So anyway, that's really all I have to say.